All right, so if you're gearing up for an exam or you just really want to understand the core principles of radar, you are in exactly the right place. We're going to break down the absolute fundamentals of how this incredible technology works, starting with the simple echo and taking it all the way to a full system detection.
Okay, let's start with the most basic idea, right? At its heart, radar is actually pretty simple. I want you to imagine shouting into a big canyon and then timing how long it takes for your echo to bounce back. Well, radar does the exact same thing. But instead of your voice, it sends out a pulse of electromagnetic energy, a radio wave, and then it listens for that wave to bounce off an object in return. Simple as that.
So, what does radar actually stand for? It's an acronym for Radio Detection and Ranging, and that name tells you pretty much everything you need to know. Its job is to answer four key questions about any target. First, is something even there? That's the detection part. How far away is it? That's ranging. And then, which direction is it and how high up is it? We're about to cover how it figures all of that out. So here's our game plan. We'll start with measuring range, because that's the most basic function. Then we'll see how radar pinpoints a target's exact location. After that, we'll look at the shout itself. The properties of the radar pulse that really determine its performance. Then we'll take a peek inside the hardware, and finally, we'll wrap it all up with a quick review to make sure it all sticks. All right, first up, range. This is the #1 job of any radar system, figuring out just how far away a target is. And it all comes down to one simple thing: timing. To measure distance with time, you've got to have a known speed, right? And for radar, that constant is the speed of light. Radio waves just zip along at a staggering 162,000 nautical miles per second. Now, keep that unit in mind, nautical miles. It's the standard for the Navy and in most radar applications. And that brings us to the magic number for all radar range calculations. If you're studying for a test, I'm telling you, burn this number into your brain. 12.36 microseconds. It is the absolute key to figuring out distance. So what is that number? It's what we call a radar mile, and the key word here is return. A radar mile isn't just the time it takes to travel 1 mile. No, it's the time for a pulse to go out 1 nautical mile, hit something, and come all the way back. That whole round trip is what takes 12.36 microseconds. And this shows you just how easy the math is. It's beautiful, really. If your radar system clocks the total travel time for an echo at 62 microseconds, you just divide that by our constant, 12.36. And what do you get? The target is about 5 nautical miles away. It's that direct relationship between time and distance. Okay, so we've nailed how far. Now we need to figure out where. To really pinpoint a target, we need a lot more than just its distance. We need its location in 3D space. Just like a telescope has to be aimed, a radar antenna gives us directional info. It uses a coordinate system with 3 key parts. We already have range. The other 2 are bearing, which is its horizontal direction, and elevation, its vertical direction. With those 3 pieces of the puzzle, you have a precise target location. Let's talk about bearing first. To be really precise, we use what's called true bearing. This is just the angle you measure clockwise from a fixed reference point, true north, all the way to the target. So, a true bearing of 0 degrees is due north, 90 degrees is east, 180 is south, and so on. It tells you exactly where to look on a compass. Now, elevation angle is the other part of the where. It's the up and down angle. It's measured from the flat horizontal plane right up towards the target. So if a target is right on the horizon, its elevation angle is 0. The main takeaway here is that when you combine range, bearing, and elevation, you know exactly where that target is. Okay, so we know radar works by sending that shout into the canyon, but the exact nature of that shout, the different characteristics of the energy pulse itself, well, that's what really determines how good the radar is at its job. These diagrams here give us a great visual for that pulse. You see, it's not just a single ping. It has specific properties that we can actually measure and control. We're going to look at a few of the most important ones, like how long the pulse lasts, how much power it's packing, and how often we send them out. First up, we've got PRT and PRF, and they're really just 2 sides of the same coin. Pulse repetition time, or PRT, is the total time from the very beginning of one pulse to the beginning of the next one. This includes the time it's transmitting and the quiet listening time for the echo. Now, pulse repetition frequency, or PRF, is just how many of those pulses we're sending out every second. And as you can see from the formula, they're inversely related. Now let's see how these three key terms really control the radar's performance. First, pulse width. That's the actual time length of the transmission. A shorter pulse lets you see things that are closer and helps you tell two nearby targets apart. Next, peak power. That's the raw energy in that pulse. It's simple. More power means you can detect targets farther away. And finally, duty cycle. That's just the percentage of time the radar's actually transmitting, which is super important for figuring out the radar's average power and making sure it doesn't overheat.
So we've got the theory down. We know how to find a target, and we know the properties of the pulse we use to find it. Now let's pop the hood and take a look at the essential hardware that makes it all happen. Think of this block diagram as our system map. It shows the whole journey of a signal through a standard pulse radar. There are 6 fundamental parts, and we're just going to follow the signal's path from the moment it's created all the way to what the operator sees on their screen. Okay, it all starts with the synchronizer. This is the heart, the timer of the whole system. It tells the transmitter when to create that big, high-powered energy pulse. That pulse travels to the duplexer, which is a really clever, high-speed switch. Its job is to direct the pulse out through the antenna. Then, the antenna listens for that echo to come back. And that weak little signal is routed by that same duplexer over to the receiver to get amplified. Finally, the indicator displays all that information for the operator to see. Fantastic! We have covered the whole journey, from a really basic concept to a complete working system. Now let's lock in all that knowledge with a quick recap of the key terms and then a few practice questions to see what you remember. All right, rapid fire recap. Let's lock these in. Range is your distance. True bearing is your horizontal direction from true north. Elevation angle is your vertical direction. The radar mile is our key timing number, 12.36 microseconds. Pulse width, PRF, and duty cycle, they all describe the pulse itself. And the 6 components that make it all work, that's the synchronizer, transmitter, duplexer, antenna, receiver, and indicator. Okay, time to test yourself. First question. How much time does it take for electromagnetic energy to go 1 nautical mile and come back? The answer is our magic number, 12.36 microseconds. Next up, what's the term for the distance from a radar set to a target measured right along the line of sight? That would be range.
Question 3. What do we call the angle that's measured clockwise from true north on the horizontal plane? That is true bearing. Okay, a hardware question for you. Which component is the switch that lets a single antenna both send a signal and receive one? That's the duplexer. And our final question, what is the term for the number of pulses a radar shoots out in 1 second? The answer is pulse repetition frequency, or PRF. Hey, if you got all those right, you've built a really solid foundation in radar principles. I really hope this explainer helped you out. Thanks for watching.